Hi, in today's video we're going to take a look at this Miniware DS213 mini oscilloscope. This scope has been around for at least a few years by now. I just never got a chance to get my hands on one until today. Miniware sent in this oscilloscope for me to do a review. As usual, you can find the product link in the video description below. Now the first thing you'll notice is just how tiny the scope is. If you recall, I reviewed the DreamSource Labs DS4T1012 on this channel a few weeks ago, and that scope is already very compact. If you put the DS213 side by side with the DS4T1012, you'll get an idea of how small Miniware's DS213 is. Although the DS213 won the size comparison, the specs are fairly mediocre. It only supports a sampling rate of 100 megasamples per second and a bandwidth of 15 megahertz. And it's actually quite pricey for its entry-level specifications. Now the DS213 does support 4 channels, and channel C and channel D are mainly for testing digital circuitry, as they have a maximum input voltage of just 5 volts. The application layer of the oscilloscope is open-sourced, so you can develop your own code and conceivably add new features to this oscilloscope if you want to. And I know this aspect may be appealing to some of the hobbyists. Because the scope is so tiny, it is not possible to physically fit standard BNC connectors in. And you can see instead, the DS213 uses these MCX connectors for channel inputs and signal output. If I were designing it, I would make the oscilloscope larger and use standard BNC connectors for channel inputs, like what DreamSource Lab did with their DS4T1012. The reason is that non-standard probes are non-interchangeable, so you'll have to carry the supplied probes around. Although the DS213 is tiny, the probes themselves are now much bulkier than the oscilloscope itself, so you can see that it makes little sense to make the oscilloscope this tiny, just for the sake of it. But I have to say, the aluminum case looks really beautiful and it feels really sturdy in your hand. Alright, now let's power it on. And you saw it took just a few seconds to boot up. Once powered up, you get all 4 traces. Now, you can configure and save your configurations, but if you don't save it, it will not remember your settings when you power cycle the oscilloscope. Anyway, this is where a touch screen would be extremely helpful. Since we only have a few controls to play with, the scope is not the easiest to use. Most of the settings are adjusted via the combination of these 2 encoders, this one and this one here. The B encoder is responsible for cycling through different menu options, as you can see here. Now I'm just scrolling it very slowly. You can see the settings are flashing. That's where you can make the change. And if you just keep scrolling, it will essentially scrolling through all the settings. And the A encoder can be used to change the current value under the highlighted menu item. So let's get to, let's just say we wanted to change the verticals of channel B. And now you can see we can change it to 0.1 volts, 50 millivolts, and 20 millivolts, 10 millivolts here. And that's how you change it. So let's say we wanted to change the coupling of channel B, and you can see we can do AC, DC. And that's how you use the 2 scroll wheels to change the settings. Although not too complicated, it does take a little bit to get used to. Now let's actually turn off channel 2 through channel 4, as we just want to concentrate on a single channel here. So let's use the scroll wheel to turn it off. And now channel 2 is off, so let's do the same for channel 3. And you can see it takes quite a bit to turn on and off the channels. So now we are left with channel 1. Now, I don't know why Miniware chose cyan as the color for channel 1 and yellow for channel 2. This is the exact opposite of the convention. I wish they would just stick with the conventional color scheme, as it can be very confusing for people who are used to the standard color assignment. Well, I'm sure this is something you could change, I suppose, if you really want to, because of the application software is open sourced. Anyway, let me plug in the probe and put a signal in and take a look. You can see this is a MCX connector. Let's plug in channel 1. And by the way, not only the connectors on the probes are non-standard, the probes themselves are non-standard as well, as there's no way for you to adjust probe compensation. As for most of the probes, the compensation adjustment is built into the BNC connector section. So when Miniware swapped out the connector, they got rid of the compensation adjustment as well. Now, I don't know why they wouldn't choose a probe where the compensation capacitor is built into the probe itself, as there are plenty out there. For example, I have one here. You can see this probe has the compensation capacitor built into the probe itself rather than the BNC end. But nevertheless, this probe is actually not that much bigger than the default probe that came with the DS213. So Miniware could have used a probe like this and kept that compensation adjustment, but they chose not to. Now, I suppose the probes could have been pre-calibrated. So let's actually take a look at a square wave signal. Now let me output a 5 volts 1 kHz square wave signal from my DG2070. Let me enable the output. And now let's try to adjust the oscilloscope settings here. And the first thing you notice is that the scope does not have an auto acquire button. In fact, you will have to adjust the horizontal and vertical settings manually. This unfortunately makes the scope even harder to use, as you have to constantly adjust the settings to just get a stable view of your waveform. But anyway, let's come here. And by the way, so right now we're in AC mode, but you can see we actually have quite a few different ones. So the AC10, this one is actually for the times 10 probe setting. So let's change it to DC10, as currently we're using DC coupling. And let's also change, let's see, I'm going to change the vertical. Okay, 2 volts per division, that looks good. And now let's come back to change the horizontal here. So, yeah. And you can see now why we needed that probe compensation. Right now we're at 1 kHz, this is a square wave, but of course, the wave is nowhere near square, and there's no way for us to be able to adjust that because there's no probe compensation adjustment on the supplied probes. Well, that is unfortunate. Now let me switch it to a sinusoidal with the same frequency, and you can see we captured that with no problem. Of course, right now it's only at 1 kHz. So let me increase the frequency to, let's say, right now it's 10 kHz, not an issue, and I do want to keep increasing it. And let's increase it to 100 kHz. Let me adjust. Let's actually adjust to 1 microsecond per division. And let's keep increasing the frequency. Let's do 1 megahertz. Okay, no issues. So let me see what is the smallest division here. It's 100 nanoseconds. Okay, so now let me keep increasing the frequency here. So now we're at 10 megahertz. And you can see that waveform started getting a little bit unstable. But we are able to measure the peak to peak and also the frequency at the bottom here. So that is good. Let's keep increasing a little bit as the scope is rated for 15 megahertz. So right now we're at 15 megahertz. You can see that is not an issue. And if I keep increasing it, by the look of it, yeah, the waveform started to degrade pretty rapidly after getting past 15 megahertz. And right now we're at 20 megahertz. You can see that this is pretty much unusable. So for a single channel, definitely we can achieve 15 megahertz. Now I'm just curious if I enable the other channels. Let's see what we got on channel 1 here. So let me go back here and enable channel 2. Okay. Enable channel 3. Enable channel 4. And it seems, let's just go back. It doesn't seem that it's impacting the channel 1 captured waveform here. So it does appear we can achieve the full bandwidth even with all the channels enabled. Alright, now for channel 1, I'm putting in a 1 MHz amplitude modulated signal. The modulation frequency is at 10 kHz and with a modulation depth of 100%. So let's try to adjust the scope and make the signal stable here. To the horizontal, and let's change. Whoa, that looks a little bit of odd. I don't think we are able to get this stable, unfortunately. So by the look of it, this is actually as good as it gets, which is not really the correct waveform here. And let's change the modulation frequency a little bit. Let me change it to, say, 1 kilohertz. And yeah, at 1 kilohertz, I suppose that is an AM signal, but you can see the triggering is just quite poor, and also the waveform fidelity is not quite there. Well, it seems this is as good as it gets. And now you can see here, I adjusted the trigger level. The waveform is a little bit more stable, but nevertheless, it has this weird modulation going on here. Now let me enable channel 2, as currently I have a 100 Hz signal coming in at 10 volts peak to peak. So let's see if we can pick up that channel 2 as well. So let's enable channel 2. So that's a channel 2 signal. Let me increase the frequency on that one a little bit. So now we're at 2 kilohertz. Actually, let's do 1 kilohertz. And as you can see, that is not awfully stable because we're currently triggering on channel 1. So let's try set the trigger to channel 2. Okay, so now the waveform is triggered on channel 2. You can see at least we get a stable display, but the amplitude modulated signal does look a little bit weird. Alright, now we're looking at a frequency modulated signal. This is the same carrier frequency at 1 MHz, and the modulation frequency is at 100 Hz with a frequency deviation of 100 kHz. And you can see the display is much better. I have to say the update rate of this scope is very fast. Now, one thing I wanted to point out is some of the settings are not very easy to adjust. For example, right now we're triggering on channel 2. If you want to triggering on a different channel, you just come here, press this middle button here, and you can see that the color changes to channel 1. So right now, in theory, if we put in a signal from channel 1, let's just do that. Let's put the same signal in. And you can see, yeah, we're triggering on channel 1. So if you, for example, go back to the triggering channel, and of course we can press this button, and you will see now it's triggering on channel 3, triggering on channel 4, and back to channel 1, and channel 2, so on and so forth. So this is how you navigate around. Now, it doesn't seem we can change the display to XY mode, unfortunately. And although it has 4 input channels, I just can't see people using all 4 input channels. You see, you've only got 2 probes out of the box. And if you need to use all 4 channels, you will have to get additional probes with MCX input connectors. Also, because the scope does not support protocol decoding, the benefit of having the additional digital channels, in my opinion, is not there. But I suppose if you do find yourself in the situation of needing all 4 channels, the channels are there. Now let's take a look at the single shot capability. For that, you can see I have changed it to single. And by the look of it, the slowest time base I can change to is 20 milliseconds. So let's use that to test the power on characteristics of a switching power supply. I have hooked up the power supply. Let's see. Yep, I just hit run, I guess. Okay, let's turn on the power supply. Okay, as you can see, we actually captured the waveform with no problem. And let's see if we can do some measurements. Now that will probably be painful as we only have a few buttons to work with, but let's give it a try. So let's see here. I wanted to, let's do V1. Where's V1? So you can see the tiny cursor on this side. Now it doesn't really have a, oh man, this is going to be painful. So let's just say, I'm just going to kind of measure V1 here. This is at our origin, and now let's change to V2, and I want to measure the top of that waveform here. So you can see, where's my delta? And I don't even see the delta of these displays here. Maybe I need to come down here and change the labeling here. So let's go down, and let's see here. Can we change that? Delta V. You can see here. So now, I assume this is V1 minus V2. Let's just go back. Oh man, this is really painful. So let's change V1. Yep. So indeed, you can see here, this is actually V1 minus V2. So we do get this 3.52 volts of the current setting here. And let's actually measure the time here. So let's go down here. And let's see, where is that? Ah, those are the little triangles down here. So let's see, we wanted to measure from the origin here to, let's see here. Oh, by the way, so if you, oh, I almost forgot. I think if you press the up button here, yeah, you can kind of scroll faster here. So that is actually at least nice. So let's just say we want to see the time difference between here and the origin here. So again, I think you have to change one of these labels here. So let's go down and let's see if we need to change here. No, this is delta V. And let's do this one. By the look of it, this is the same one. So okay, so let's go to this one here. Yep, delta T here. So that's 85.3 milliseconds between marker 1 and marker 2. Now this is a little bit of hard to see. I wish they have some kind of subtle lines here instead of just these arrows. But anyway, you can see that we can do some measurements, but it's just very painful because we don't have enough buttons to work with. I almost forgot to show you. In single shot mode, you can actually scroll through the captured memory here. As you can see, we do have quite a bit of a memory depth. So to do that, we are going to go to the X position. And now we can use the scroll wheel to scroll through. Now this is going to be very useful if you are capturing some kind of non-repeating events. And this is exactly what the single shot is for. So you can see that this implementation is actually very good. And also there's some basic settings you can control. For example, you can come here and you can save the current waveform and whatnot. But also you can come here to set, for example, the volume, which I set it to 10% as I find it very annoying. But if you want to, for example, change the beeping to be louder, you can actually adjust it here. So let's change it back to 10%. And of course you can change the backlight. And when you're satisfied with the setting, you can press this button here, and that's the K3. And to confirm the settings, you can see that that's completed, means it's actually saved. Anyway, so that's just some of the basic operations of this oscilloscope. The DS213 can also be used as a function generator, and it can output a square wave signal up to 8 MHz, and output sinusoidal, triangular, and sawtooth signals up to 20 kHz. Now, there are some limitations, as the output voltage is set, fixed, at 3 volts and cannot be adjusted. Also, the frequency can only be adjusted in intervals of either 125 or 2468, depending on the frequency. So, for example, right now we're displaying a square wave, and let's take a look at the frequency here. You can see currently it is at 10 kHz, and we can increase it, let's see, to 20, and you can see there's nothing in between 20, 50, and 100. So let's actually change it to 8 MHz and see what we got here. And it's actually not all that bad. And by the way, the rising edge here is unfortunately limited by the function generator on this DS213. As you can see, if I change the frequency lower, you can see that the rising edge does not change. So that's the function generator. And of course, we can change to different waveform types. So let's actually change to, let's see here. Change to, this is a sawtooth. Reduce the time base a little bit. And now we're showing a sawtooth at 20 kHz. Actually, that's not bad. So let's change it to a triangular waveform and a sine waveform. So now there are some artifacts. I wondered if the DAC here used is not a 8-bit. As you can see, we have quite a bit of artifacts here. Let me just zoom in, you can see that. I'm not sure what kind of output DAC is used in this DS213, but you can clearly see the quantization here. So this looks to me, it is at most a 7-bit DAC. As you can see, we have significant quantization artifacts here. And now let's open it up and take a look inside. And by the way, the Allen key for the screws are even supplied by Miniware. And let's first take a look at the current consumption of this oscilloscope. So let me power it on. It looks like at medium brightness we're only enjoying about 180 milliamps, so that's actually quite good. So let's take a look at the battery capacity here. And this is a 3.7 watt hour, so it is 1000 milliamp hour. So at roughly 200 milliamps, you can do the math. That is roughly 5 hours of runtime, which is really good. Alright, let me first remove the battery. And not sure if you can see this. If you take a look, the battery connector is definitely very interesting. Because there's not enough height, you can see the battery connector is bent over at an angle so that it can fit inside the case. Now, as I mentioned earlier, other than making a statement, it's really not necessary to make this scope this tiny. And by the look of it, we also have one additional screw here, so let me remove that one. And we should be able to open it up. So it looks like the top board here is only for these rotary encoders. And you can see the knob is actually at the bottom here. Actually, let's take this out before we lose them. And you can see this encoder board makes contact with the main board via these spring-loaded board-to-board connector pins right here. Anyway, let's take a closer look at the main board. Judging by the component density, this is at least a 4-layer board. And by the way, I will upload all the teardown pictures to my website, and I will leave a link below so you can check them out. Now, the layout is definitely very neat. Towards the left, that's our two main input channels, A and B. Now you can see we have two of these AG1KLP Q48 FPGAs. These are low-cost, low-power FPGAs, and they only have up to 1280 logical units each. And the ADC used here is an MXT2088. This is an 8-bit 100 megasamples per second ADC, and it has two independent channels. The MCU used in this DS213 is a GD32F303VT6, which is based on ARM Cortex-M4, which is a relatively powerful microcontroller. And here in this section, we have two of these 4051 8-channel multiplexer demultiplexers, and also a couple of 4053 triple 2-channel multiplexers. Now, towards the digital input area, we have four of these CPC 1017N digital relays. We also have a couple of these GS8052 250 MHz rail-to-rail output op-amps, and I'm pretty certain these are used as the front-end amplifiers for the input channels. Now, I think these are actually used for all the input channels, including the two main input channels, as there are no obvious front-end circuitry near the other end. I took a look at the reverse side before and confirmed there is no additional circuitry on the back side of the board. So if this is the case, it would be less than ideal, as the analog signal would actually travel across the board to get amplified. And even with a multi-layer board and the shielding between the ground planes, it could still pick up some noise from other parts of the circuitry. Now, the good news here is that the outer case is aluminum, so it does significantly reduce the EMI from the outside. And by the way, reassembling this unit requires quite a bit of patience and precision, as the four buttons up here, as you can see, the plastic buttons, these are held together by cap-down tape at the reverse side here, and they're not very easy to be held in place. And also, the button on the left here, you can see the cap falls off easily. And everything needs to be held in place before you can put the board in. As you can see, the fit is very tight inside this case. It literally took me 15 minutes through trial and error before I could put everything back in. And even though I was very careful, I still managed to trap a couple of dust particles on the LCD side. Oh well. That's pretty much what I wanted to cover in this review. In my opinion, the DS213 is really geared towards a niche market. Now, there are a few reasons why you might consider this oscilloscope. One is perhaps you live in a tiny apartment in a big city and just absolutely don't have any space to spare. And if that is the case, and you find yourself needing a bare-bone entry-level oscilloscope, you might consider this DS213. Although I would suggest you taking a look at my review of the Dream Source Labs DS4T1012 portable oscilloscope I reviewed not too long ago. And that one is slightly bigger, but still very small, and significantly more powerful. For all seriousness though, if you like to experiment and get into programming embedded systems, this might be a good platform to get your feet wet. And at the same time, you also get a functional oscilloscope. Anyway, let me know what you think in the comment section below. I hope you enjoyed the video and teardown. If you liked the video, please remember to give it a big thumbs up and remember to subscribe to the channel for more videos like this in the future. Thanks for watching. I will catch up with you next time.